Welcome to this explainer. Today, we are cracking open the fascinating black box of mass analyzers. We're going to treat these incredible pieces of scientific equipment exactly like what they are: ingenious, microscopic obstacle courses. We'll be zeroing in on mass analysis, which is the highly specialized tech used to separate ions based entirely on their mass-to-charge ratios. We're going to explore magnetic sectors, double-focusing instruments, linear quadrupoles, quadrupole ion traps, and time-of-flight analyzers. Getting a grip on how these tools actually work is absolutely crucial because, well, they're the engines driving everything from cutting-edge pharmaceutical development to environmental monitoring. So let's dive into some truly beautiful physics. Here is our roadmap for today. We'll kick things off with the ultimate sorting challenge: hit magnetic sector analyzers, double-focusing instruments, quadrupoles and ion traps, then time-of-flight analyzers, and we'll wrap it all up by looking at how to choose the right tool for the job. Let's get to it. Part 1. The ultimate sorting challenge: separating the invisible. The fundamental problem we face in mass spectrometry is this. After molecules get bombarded with energy and ionized, they turn into a completely chaotic, mixed-up beam of charged particles. You've got heavy ions, light ions, and everything in between, all flying together. But before we can detect a thing, this invisible stream has to be perfectly sorted by their mass-to-charge ratio, or M/Z. That sorting process, that is the beating heart of mass analysis. Picture the scene right after the ionization chamber. We have a newly created, incredibly fast-moving ion beam blasting out into the vacuum through a highly specific focusing slit. It is completely unsorted and hurtling straight toward the first of our engineered obstacle courses. Think of that narrow slit as the starting gate. What happens next depends entirely on the specific physics we decide to throw at it. Moving on to part 2, magnetic sector analyzers, the curveball. Let's look at our first solution, which leans on some classic magnetic physics to quite literally bend the path of those flying ions. By hurling our ions through a massive, powerful magnetic field, we actually force them to curve. The math tells us that the radius of that curve depends directly on the mass of the ion, meaning heavier ions are going to take a much wider path. So the magnetic field is acting exactly like a physical filter. Because the analyzer tube is built with a fixed curve, only ions with the exact right mass-to-charge ratio can successfully navigate the bend to reach the detector. Lighter ions curve way too sharply and smack into the inner wall. Heavier ions don't curve quite enough and hit the outer wall. By continuously varying the strength of that magnetic field, kind of like turning the tuning dial on an old radio, scientists can seamlessly scan through and detect every single different ion, one by one. Now, the absolute key concept here is resolution. Think of resolution as the instrument's visual sharpness, how well the machine can distinguish between two ions of very similar mass. If you have an ion at a mass of 1,000 and another slightly heavier ion right next to it, resolution is what determines whether you see one big blurry peak or two crisp, distinct signals. A standard magnetic sector can actually approach resolution values of 10,000, which is honestly fantastic for most broad applications. But as we know, cutting-edge science sometimes demands even sharper precision to tell almost identical molecules apart. Which brings us right to part 3, double-focusing instruments, sharpening the image. This is a really clever upgrade designed specifically to boost that resolution metric to the next level. So the reality of standard magnetic sectors is a slight physical imperfection. Ions don't actually all leave the starting gate with the exact same initial velocity. Some get a little extra push, others lag behind just a bit. In a simple magnetic setup, this tiny velocity spread causes the final image at the detector to blur, which ruins our resolution. To fix this, engineers came up with double-focusing instruments. They added an electric field region, an electric sector, either right before or after the magnet. This forces all the particles to travel at the exact same velocity before the final sorting even happens. It's a simple but totally brilliant addition that tightens up the ion beam and improves the resolution of the mass analyzer by a phenomenal factor of 10 or more. All right, part 4, quadrupoles and ion traps, the electric obstacle course. We are now shifting away from magnets entirely to look at how precise radio frequencies create a totally different type of gauntlet. Welcome to the quadrupole. Imagine the linear quadrupole as a brutal corkscrew tunnel. It uses 4 parallel solid rods, applying both direct current and radio frequency voltages incredibly precisely. This whips up a rapidly oscillating electrostatic field that furiously pushes and pulls on our charged particles as they fly through. If an ion has the exact right mass for the current voltage, it survives, undergoing a perfectly stable corkscrew-like trajectory right down the middle of the rods, straight to the detector. But if its mass is even slightly off, that push and pull becomes wildly unstable. The ion's path gets wider and wider until it violently crashes into one of the solid rods and is instantly neutralized. It's an amazingly effective, lower-cost filter that you'll find in most lab benchtop instruments today. Now, let's contrast that linear setup with its closely related cousin, the quadrupole ion trap. The linear quadrupole filters ions in flight, letting them pass through the tunnel one by one while the rest are destroyed. But the ion trap, it captures and holds all the ions at once. It uses a donut-shaped ring electrode and two end caps to trap ions of all masses simultaneously in concentric, three-dimensional oscillating trajectories. They just sit there buzzing around in a tiny cloud. Then, by carefully sweeping the radio frequency potential, the trap intentionally destabilizes them, ejecting them out sequentially toward the detector, one mass at a time. But there's a catch. Because the ion trap holds absolutely everything at once in such a highly confined space, you can get a quirky phenomenon known as self-chemical ionization, or self-CI. Basically, overcrowding in the trap leads to random physical collisions between uncharged neutral molecules and those fast oscillating ions. These impacts can actually transfer protons around between the molecules, effectively changing their mass right before our eyes. If we aren't careful, this can totally complicate our data with abnormally large M+H peaks. It's just a great reminder that when our invisible obstacle course gets a little too crowded, it can literally change the runners in the race. Next up, Part 5, Time-of-Flight Analyzers, the drag race. Let's explore what might honestly be the most elegant solution of the bunch. This method ditches the complex oscillating radio frequencies and massive magnets entirely, relying simply on kinetic energy and raw velocity. The time-of-flight, or TOF, analyzer is a literal microscopic fit race. The rules are beautifully simple, playing out in 4 clear steps. First, all ions are pulsed into the starting line at the exact same microsecond. Second, they're accelerated by an electric field that gives every single ion the exact same kinetic energy. Third, because they all possess identical energy, the lighter ions inherently travel faster down the long, empty vacuum drift tube. And finally, step 4. Those faster, lighter ions hit the detector first. If everyone gets the exact same energetic push at the starting line, the lightest runner is physically guaranteed to win. The sheer genius of this design is right here in the core math. The flight time is directly proportional to the mass. That means simply by precisely measuring the time it takes an ion to hit the finish line, which we measure in fractions of a microsecond using insanely fast electronics, we instantly know its precise mass-to-charge ratio. There's no scanning through frequencies or fields required at all. We just measure the time it takes to cross the finish line. Because of this incredible speed, the structural simplicity of just using an empty tube, and the complete lack of restricting magnetic fields, TOF basically has no upper weight limit. It's used in the real world to analyze massive biological molecules, complex proteins, huge polymers, critical antibodies, stuff that would simply be way too heavy for a standard quadrupole to even handle. Plus, it can be miniaturized. During the 1991 Gulf War, the U.S. Army actually deployed tracked vehicles equipped with mobile TOF mass spectrometers to rapidly test the air for chemical warfare agents. And today, you walk right past basic TOF instruments at airport security checkpoints when they swab your luggage for tiny traces of explosives in real time. It's everywhere. Finally, Part 6, Choosing the Right Tool. Let's wrap things up and see how all these distinct mass analysis technologies actually stack up against one another. When we put all these options side by side, it becomes pretty obvious that there is no single perfect mass analyzer. Every single instrument represents a trade-off. If you need absolute precision and the highest possible resolution to separate nearly identical masses, you can probably justify paying the premium cost for a double-focusing instrument. If you just need a reliable, highly sensitive, affordable lab workhorse for your daily tasks, the linear quadrupole or ion trap is going to be your best friend. And if you're studying massive proteins or need ultra-fast analysis without mass limitations, time of flight is definitively the way to go. Ultimately, it's all about choosing the exact right physical sorting technique for your specific scientific need. That wraps up our explainer today, but it does leave us with one really fascinating thought. We have gone from heavy magnets to oscillating radio frequency corkscrews, all the way to microscopic drag races measured in nanoseconds. As our scientific targets continue to get bigger, heavier, and vastly more complex in the years to come, what ingenious, invisible obstacle course will we have to invent next? Thank you so much for exploring these incredible technologies with me today. Keep asking questions and keep exploring